Okay, this is the material from chapter 16. And in this chapter, we're going to study how to estimate labor supply models. So an important context in which earnings are partially observed is in modeling people's labor supply decisions, where we only see earnings for those who choose to work. And the type of modeling framework that we're going to consider in this chapter assumes that the decision to work is actually voluntary. So it's assuming that you could, not work or work, and everybody is just choosing in one of those states. Okay, there's a different class of models that has involuntary unemployment, but in this type of model, all unemployment is actually voluntary. It's basically saying that there's some wage at which you could work. So it's kind of like a fallback option, like you could always work at McDonald's or something. And some people choose not to work because they don't want to work at that wage that they're offered. Okay. Okay, so what's the model? So in this type of models, individuals accept a wage if the wage offer exceeds what's called their reservation wage. And the reservation wage is the minimum wage that a person would be willing to accept. So maybe your reservation wage is $15 an hour, and you don't want to work for less than that. You'd rather stay home. Okay, so everybody has some reservation wage, but we do not usually see what it is. So we're actually going to model what it is. Okay, so WI denotes the wage offer. So the idea is that a person gets an offer in the labor market, and then they would choose to work if that offer exceeds their reservation wage. Okay, and different people have different wage offers, depending on their characteristics. So somebody with more education would get a higher wage offer. And then different people have different reservation wages. So for example, someone who has a lot of children at home that they have to take care of, they may choose not to work unless the wage is pretty high because they have a high reservation wage. Okay, so if somebody's not working, it could be either because they got a low wage offer or because they have a high reservation wage, or both. Okay, and we're going to assume that the wage offers depends on some characteristics, XI. So usually XI includes education and labor market experience. Those would be standard variables you'd include in a wage regression. And the reservation wage is assumed to depend on some characteristics which we can call ZI. And ZI and XI could overlap. Like, for example, education could affect the wage offer as well as the reservation wage. But ZI might also include other factors. Like, for example, a woman's decision to work might depend on her husband's earnings. Okay, so in that case, ZI would include husband's earnings, but her own wage offer, like the offer that some employer makes, might not depend on her husband's earnings, right? There's no reason that the employer would care so much about her husband's earnings. So sometimes, we have reason to think some things belong in X, some things belong in Z, and some elements could overlap. Okay, so let's write down two equations. So this is going to be the equation for the wage offer, and this is the equation for the reservation wage. And then in the data, we will only see wages for people who choose to work. Okay, and also I'm going to assume that we don't know the reservation wage. So we will not see that directly. There are some surveys that actually elicit reservation wages. Like they might ask people, what's the minimum wage that you would accept to work? But usually surveys don't include that information. So we'll just assume we don't see the reservation wage. Okay, and then DI is going to be an indicator variable that equals 1 if a person works and otherwise equals 0. Okay, so the model for the decision to work, DI equals 1 if the wage offer exceeds the reservation wage. DI equals 0, if you don't work, and that means that the wage offer was less than or equal to the reservation wage. The equal doesn't really matter because we're assuming everything's continuous, so the probability it's equal, would be 0 basically. Okay, now to complete the model, we need to state the assumptions we're going to make on the error terms. Okay, and these are crucial. So we'll assume that the error term, so look back at epsilon is the error term for the wage offer equation, and V is the error term for the reservation wage equation. And we'll assume that those error terms are jointly normally distributed, and this is the variance-covariance matrix. Sigma squared epsilon, so that's the variances, and it could have some covariance. Okay, we won't rule out, we won't impose that this is zero. It could covary. Okay, so the goal of the estimation is to recover all the structural parameters of the model. Okay, so these are basically all the parameters. So when we look at the parameters, what are the parameters? They're beta, gamma, and then these are also included as parameters, these variances and the covariances. And if we can get all these parameters, we can actually use this model to do policy experiments, okay? So for example, we could say, how would working behavior change when wage offers change? Like, for example, suppose the government subsidizes wages for some people. There are some government training programs that are basically wage subsidy programs. They would increase your wage by $1 or $2 an hour, okay? And you can say, how will this affect working behavior? Or you can say, how does working behavior change if, for example, we forced everybody to get a high school degree? So we changed their X's, we changed their Z's. So the types of policies we can do is anything that changes the wage offer or things that change the reservation wage. Like, for example, maybe the price of childcare might be a factor affecting your decision to work. So if you give a subsidy for childcare, maybe then people would choose to work. Okay, so childcare price of childcare could be one of the Z's, for example. Okay, so consider, well, we only see wages for people who work. Okay, so even if we assume that E of epsilon given X is equal to 0, which is like a standard assumption, that we're not omitting variables in the wage equation, we would expect that E of epsilon given X and given D equals 1 is not equal to 0. And the reason we would expect that is when we condition on D equals 1, we're basically conditioning, because when this conditional expectation means we're conditioning on this. This is true, D equals 1. Well, when D equals 1, that means the wage offer is greater than the reservation wage, which means that E epsilon is greater than this. Okay, so E of epsilon, if you know epsilon is greater than this, is probably greater than 0. It's not going to be equal to 0. So this assumption does not guarantee that this would equal 0. Because normally people would work if they have an unusually high epsilon. That means that they, had a very good wage offer, then people would work. Or if they had an unusually low V. Okay, so E of epsilon given D equals 1 is not equal to 0. And this means that you have an endogeneity problem. If you would just estimate the wage equation using workers, this will give you a bias problem because there's endogeneity. Okay, so in 1976, actually there's even an earlier paper in 74, James Heckman proposed a method to control for selectivity bias in estimating the parameters of a labor supply model. Okay, and this method proceeds in 2 stages that we'll talk about. It's actually called the 2-step method because there are kind of 2 stages to the estimation. In 2000, he actually received the Nobel Prize, largely for his contributions to understanding the sources of selectivity bias, like in these types of models, and for developing methods that can be used to eliminate selectivity bias. Okay, so he was actually my advisor when I was in graduate school, and I was actually with him when he received the Nobel Prize. So I'm kind of going to describe to you, I mean, he's done a lot of different research in different areas, but I will kind of describe to you some of the early work that he's famous for in terms of estimating these labor supply models. And you'll see it's closely related to the Roy model that we talked about earlier. I mean, in some ways, even this model is a little bit simpler than the Roy model. Okay, so let's rewrite this model, the wage equation, in this way. So here, all we're going to do is we're going to add this mean and subtract this mean. Okay, so we added this and we subtracted it. So you basically add 0. Okay, so this ui is defined as this term in brackets. If I take e of u given x given d equals 1, that equals 0. That's by construction, basically. This has conditional mean 0. Okay, so that tells you that if I could find an additional regressor for this term that I could include in my regression, my wage equation, then I could estimate the wage equation only using data on workers. Okay, so the goal here would be to find this regressor. Okay, and this is sometimes called a control function because it's a function that we include in the regression to control for selectivity bias. I mean, it's a function of x and also of this index that determines the d. And under the assumptions that we made about the error distribution, like being joint normally distributed, you can actually figure out what this regressor equals. Okay, so, and that's what this is going to do. So this is going to show you what is this function. Okay, the spacing is a little bit odd because this equals sign should be above this one, but just bear with me. All right, so if I put in for d equals 1, that means WI0 is greater than WIR. The offered wage is greater than the reservation wage. Okay, now we plug in for the offered wage, plug in for the reservation wage. Okay, and then we can rewrite this by moving everything that's observed to one side, everything that's unobserved to the other side. And then we're also going to divide through by sigma star. So you see if we write it this way, we have vi minus epsilon I, and we're going to divide through by sigma star, which is the square root of the variance of vi minus epsilon I. So this is to get it to be a standard normal. Okay? And now we still need to just write down what this is. So let eta I equal this ratio here. Okay, and notice that eta I is standard normal because we divided by the square root of the variance. And remember, two normals, the difference between two normals is normal. Okay, this is like a property of the normal distribution. So we know that vi minus epsilon I is normally distributed. Okay. And then just to save our notation a little bit, we'll call this here ci. Okay. Okay, so now in this a little friendlier notation, we can write it this way. And then we're going to use some results about like the mean of one normal random variable conditional on, a property of another normal random variable, okay? So I'm not going to derive this because it just takes a bit of work to show this. I mean, I have some handouts in my office, but it's kind of pages of like integration and things to show this. But But E of epsilon given eta is less than C is, you can write it as a covariance between epsilon and eta divided by the variance of eta, okay? It's a little bit like if you did a regression of epsilon on eta, okay? Times E of eta given eta is less than Ci. Okay. All right, and then that's equal to covariance of epsilon and Vi minus epsilon here. Now notice sigma star is just a number. It's not a random variable, so we can just pull this out. And then the covariance of this is going to be sigma epsilon V minus sigma squared epsilon. Okay, this here. And for this part, we'll use the results about truncated normal random variables that we had in the Roy model set of slides. Okay, I think that I reproduced them here, but these formulas can also be derived, but I just, it takes a bit of work to derive them, and it's not that much fun doing integration. So, so I'm just going to give you, these are like properties. You can kind of memorize these, okay? Well, the final will be open note anyway, so you don't have to memorize them. So E of eta given eta less than C is this. Okay, so eta is normal 0, 1. So imagine if we have a normal 0, 1 random variable and we truncate it from above. This is taking like the mean, but so you draw from a normal and you take the mean, but only below a cutoff. Well, if it's normal 0, 1 without truncation, then if I take the mean with the truncation, it's going to be less than 1. So that's how you know it has to have a minus sign. And this is just the density of eta, but because we're doing this conditioning, you divide by the probability that eta is less than C. This is that probability. Okay, and if you truncate it from below by C, and this is truncation from above, this is truncation from below. Okay, so if you truncate it from below, you get this equation. Okay, using these results, we can write the wage offer equation in this way. Okay, where this, well, get back to here. This is the alpha. So we just got expressions for this. Okay, this is the truncation from above, right? And we're going to plug that in. And so this alpha here is sigma epsilon V minus sigma squared epsilon over sigma star. Okay. So the only thing, so now this would be the extra regressor that you include in the wage offer equation. So the only thing now is how do we obtain this regressor? Because it depends on Ci. So look back at Ci. And Ci depends on some unknown parameters here. Right? This is Ci. And it depends on beta, gamma, sigma star. Okay. So we need to estimate Ci so that we can form this Mills ratio. Okay, so how do we get this Ci? So, and this is why it's called a two-stage procedure, because actually the first stage is you get this Ci, and then the second stage is you form this lambda Ci. Okay, so you asked me a probit model for the decision to work or not. Right, so, and that'll give you Ci. That's step 1. That's like stage 1. So if you write down what's the probability you work given x and z, that's just the probability that the wage offer exceeds the reservation wage. Let's see if I wrote it down here somewhere. I'm not sure if I wrote it, but that's, it's a probability that this is true, okay? And if I estimate a probit model, I will get beta minus gamma over sigma star, okay? So here's a probit function. So I can get beta minus gamma over sigma star. And for the x and z's that overlap, I only get beta minus gamma. I cannot separate out the beta from the gamma, okay? But I get this beta minus gamma over sigma star, like all in one. Okay, so I could get beta over sigma star, gamma over sigma star, but if x and z overlap, I get beta minus gamma over sigma star. And then I form this regressor. Okay, now step 2, because it's called the two-step estimator, step 2 is I include the estimated control function as an additional regressor in the wage equation. So once I have CI here, I put in the CI hat and I get lambda CI hat. Okay. And now I do this estimation and I obtain an estimate beta hat. Okay. So basically I form this regressor. Now I run this equation, and from this regression, only using the data on people who work, only using their wage data, then I can get beta and alpha from here, okay? So remember from the probit model, I got beta over sigma star. And here I'm able to get beta by itself. So that tells me I can back out the estimate for sigma star. Okay, and given that I now have sigma star, I can also go to the probit model where I got gamma over sigma star, and I can back out the estimate for gamma. Okay, you have to sometimes do a little bit of detective work trying to figure out how am I going to get all these parameters. You know, it's a little bit of creativity here. So I get beta from the wage equation, go back to the probit estimation, back out sigma star, then I go over to the gamma over sigma star and I back out the original gammas, okay? So you can see that, you know, I can get almost everything. And then I also get an estimate at alpha, which equals sigma epsilon v minus sigma epsilon star, and I know sigma star. Okay, so that means that I can estimate this difference. All right, so that's just how I get all these parameters. Now, how would I use this model to evaluate effects of some policies? All right, suppose that the government wants to give a wage subsidy to people who choose to work. What will be the effects of the subsidy on the proportion of the population that chooses to work? Okay, so now basically the wage offer has increased for everybody. It increased by tau. So I need to know what's the probability that this wage offer exceeds the reservation wage. All right. And so again, just move everything that's unknown to one side, the epsilon, and everything that's known on the other side. So tau is known because let's say the government gives $500 to each person or something. Okay, so we know tau. And so this would be the probability that people work given the subsidy. And I can calculate this. So if I know beta hat, you know, from my previous estimation, I have beta hat, I have gamma hat, I have sigma star hat, and then tau is something I know, like the government says $100 or $200, and I can figure out for different values of tau, how would that affect the probability of working? Okay, we can also examine the effects of the subsidy on the mean wages of people who choose to work with the subsidy. Okay, so this is, well, this is with the subsidy, you basically do everything that we did before, but you just add in this tau here. Okay, and so that means that CI, what I called CI before, is now CI tau. So this cutoff will change. Okay, but I can still compute the expected wages given that you're working, with the subsidy. All I have to do is compute a different CI for everybody, and then because otherwise I have all these parameter estimates. Okay, so given the estimates, we can evaluate the effects of a wage subsidy on average wages for workers in a range of subsidy values. And we can allow the subsidy to be worker specific. For example, if a government program provides subsidy only to certain workers. So some people might get zero subsidy, some people might get a different big subsidy. People could have different subsidies, and you could do all this same policy analysis. Okay, now this is another example of a different policy. Okay, so we considered a wage subsidy policy. So now we're going to look at what if they impose a wage tax instead of a subsidy. Okay, so if people before received W, now people get tau times W. Okay, so the tax that they're paying is 1 minus tau times W. So tau would equal 0.9 if the wage tax is 0.1. So what will be the effect of this tax on the probability of working? Okay, so it's a little bit different because now it's proportional. Okay, but I can still write down what's the probability you work. Well, it's a probability, now your wage offer is multiplied by tau. Okay, so I have this, but it's just multiplied by tau. But see, this part is not multiplied by tau because it didn't affect the reservation wage. So just this part is multiplied by tau, right? Only everything to do with the wage offer. So this tau. Okay, and so this would be the probability that you work with the wage tax. Okay, and the sigma is actually going to be different because the sigma, well, it's going to be a little different because the sigma now has this tau. So if I compute the square root of the variance of this difference, it would also have this tau entering in. But as long as I know tau, I can figure out what this is. Okay, and we can also look at how it affects mean wages. This is the expected epsilon given that you choose to work. Right? Okay, so, sorry. This is, yeah, so if you choose to work, that's what it means with the tau. Okay, and I'm assuming you did the first stage estimation, so you have beta, you have alpha, you've got gamma, you have all the ingredients. And then you can calculate what would the expected wage be if there was a tax on wages, right? So you can do this policy analysis even if there was no tax in reality. You're considering different policies. Like you're considering a wage subsidy, you're considering a tax, but you haven't imposed those yet. Okay, so you can evaluate effects of imposing a hypothetical wage tax. Okay, and you can also use the model to figure out how much tax revenue the government would collect. Because if they impose a tax, fewer people are going to choose to work, and so government tax revenue would go down. Okay, so that's the last slide. So I realize there's a lot in this chapter. I hope this is helpful for, kind of figuring out what some of the steps are, but we will also go through it in class.